I'm going to continue with phenomenological force models a little bit. I will note that all of this stuff that I'm talking about is also written up in the sort of abstracting Act 3 stuff from ModSim. So if you feel like going back and reminding yourself on those notes, that's another version of the same stuff. But since I'm doing videos for this class, I thought I would do this, do these things as well. Okay, so we talked about friction as phenomenological forces. Continuing with the phenomenological forces, let's think about drag and lift. Now, the sort of situation for both drag and lift are cases where you have some object. So let's draw, just for the sake of argument, we'll draw an airfoil. So that's the side of an airplane's wing, and that object is moving through some fluid, and so I'm going to draw some sort of streamlines here to indicate that you can sort of imagine this airfoil being in a wind tunnel, for example. Okay, and you could draw the same thing for lift. So they're the same types of situations, but they're actually two different kinds of forces. The drag force is the force that basically has to do with the object pushing through the medium. Okay. And what the lift force has to do with is that when you have an asymmetry when you're moving through the medium, either maybe the airfoil has a different sort of top contour than bottom, or maybe you have a ball that's rotating and so the top is moving in a different way relative to the medium than the bottom. Lift is the force that actually is not due to pushing through, but it's due to differences across the medium that's perpendicular to the velocity. So drag, if we think about magnitude and direction, drag is going to be opposite the motion, right? So in the minus v hat direction. And lift, on the other hand, is going to be perpendicular to the motion. And so I'll first just write perpendicular to v hat. Another way of thinking about that is that if I'm confining the motion to the xy plane, right? So this is what my velocity is, right? I could also say that the lift must be in the k hat cross v hat direction, either plus or minus the k hat cross v hat direction, depending on what the orientation of the object is. Because if you think about it, v hat is in this direction, k hat is coming out of the page, so v hat crossed into k hat actually would be pointing down. So probably in this case, since given how I've drawn the airplane wing, it actually ought to be minus k hat dot v hat as a direction. You'll note that k hat dot v hat is always going to have magnitude of 1, so this is a sensible direction to write, and by the same token, obviously v hat, by definition, has a magnitude of 1. The magnitudes of these forces actually are pretty complicated, and there are a lot of different models that you'll find for it. So for example, if you look up drag on a golf ball, you'll find all kinds of really complicated graphs about how that drag force changes depending on velocity and depending on how many dimples there are on the ball and all kinds of other stuff, right? So these are complex forces, and they're complex because you're actually capturing very complicated fluid dynamic stuff around the ball, when in the end, of course, the fluid dynamic stuff is due to very complicated motion of atoms and electron wave functions changing and so on at the very microscopic quantum level. So they're complicated forces. Typically, we use a couple of different kinds of models for these. Often drag is modeled as depending on a number of things. So if you actually write a full expression for the drag force, including the direction, it'll look something, an expression you'll find a lot is this one. So 1/2, so it's a constant. C sub d is what's referred to as the coefficient of drag. And what this has to do with is what's the shape of the object that's moving through. So this is a dimensionless number, and any kind of object moving through a fluid is going to have, you could define the drag coefficient for that object. Typically, drag coefficients are somewhere between 0.1 to 1, and it's dimensionless. A here is the cross-sectional area, so it's the presented area. you'll notice that is going to have units of meters squared. And when I say the presented area, what you're asking is, if you were to look at this object sort of head on, sort of look at it along this velocity vector, what's the area that you would see in that direction? So it's not, the area here is not this area, it's actually this area. So if you sort of think about looking at this wing head on, if I turned it head on, it would look something like that. And this would, what you would see head on would be the area, right? So it's sort of the length of the wing times the height of the wing in this particular case. So that's what you mean by the presented area. Rho is the density of the fluid. So that's kilograms per meter cubed. And finally, v squared is the magnitude of the velocity squared. Now that's not always the model that you want to use for drag, but it's often appropriate for things that, say, are moving through air. So for example, if you're modeling drag on a baseball, this is not a bad model. It's not a perfect model either, but it's okay. You also will find situations where you might want to model drag as simply being proportional to the velocity. So you'll also often see other drag models that say the force of drag is, minus some constant. So I'll just say beta times the velocity. That again is opposite the direction of the velocity, but now it's some constant that's just times the velocity. So instead of depending on the velocity squared, it just depends on the magnitude of the velocity. That's maybe a more appropriate model for cases where you're moving through a thick fluid. So this is what's often referred to as a viscous drag model, whereas this is what's referred to as an inertial drag model. Lift is also pretty complicated. And I think the key things to note about lift are that lift often also has, and I'll just note it, since it depends so much on what situation you're talking about, it's often proportional to v squared in the same way that drag is proportional to v squared. It usually has an area that's involved. That area has more to do with what the sort of lift area is. I don't think it's actually probably important right now to give you an expression for lift because it depends so much on what type of situation you're talking about. But an example of lift would be the Magnus force that you may have encountered back in ModSim. Right? In the case of the Magnus force, that Magnus force depends on how fast the object is spinning, so it's called omega, and also what the velocity of the object is. So Magnus force would be an example of lift, and you can see this is going to be perpendicular to the velocity because of the fact that there's this cross product, and it also kind of has a v squared dependence to it in that omega, the sort of speed of the spin, tells you something about how fast the object is moving relative to the fluid, or the surface of the object is moving relative to the fluid. So that's lift and drag, mostly drag because I think lift is going to depend on the situation you're in a little more.